In this video, we're going to continue our analysis of partial fraction decomposition. We're going to look at situations where the denominator of our rational expression that we're trying to break down has repeated linear factors. So let me give you a quick reminder of what the easiest partial fraction decompositions look like, and then we'll look at what happens when we include a repeated linear factor. So before, when we were doing partial fraction decomposition, we would start with a proper rational function whose denominator was split into a few different pieces. So let's just use two pieces right now to get the idea. So suppose I have a rational function like that. It's pretty simple, but the denominator has two different factors, two different linear factors multiplied together. What we did before when we were doing partial fraction decomposition was to introduce one piece or one term for each of the terms that appeared in the denominator. So the proposed partial fraction decomposition, the way we would say that we would want to split this into pieces, would include one piece for each factor that we saw. So we'd see in a over x plus p and a b over x plus q. I'm thinking about p and q as being known constant parameters like 1, 2, or 3, and x as being the variable in this rational expression. So our partial fraction decomposition was to take the big thing, propose a way to split that into pieces. The pieces were depended upon the terms or the factors that appeared in the denominator, and then we converted this to a polynomial and solved a set of algebraic equations to figure out how much of each piece we needed. So in this situation, what I want to do is consider what happens if we have repeated linear factors. So what I mean by repeated linear factors is one of the pieces in the denominator, when you write it out in factored form, is raised to a power higher than 1, like a square or a cube or something like that. And when we see this type of feature, this type of pattern in our denominator, it changes the way that we split up the partial fraction decomposition. It forces us to include more pieces to cover all the possibilities. So just as kind of a model example, let's just look at one of these factors being repeated twice. So suppose we're trying to break down this polynomial x plus p, x plus q squared. The x plus q squared is a repeated linear factor in the denominator. And what I want to do to take that into account, what I want to do to allow that to deal with the situation is I'm going to include one more term in my partial fraction decomposition. I'm going to try to allow one more piece that I can build from. It's going to have the same structure as the other pieces, except now I'm going to put x plus q squared in my denominator. Okay? So when you have a repeated linear factor, that forces you to include two terms in your partial fraction decomposition. One piece for each power of that repeated factor. If we had x plus q cubed, that would force us to include one more term in our partial fraction decomposition. I'd write this as x plus q cubed. So as the power here gets repeated more and more times, as we get higher and higher powers of this linear factor, we would include more and more pieces in our partial fraction decomposition, just to cover all the bases, to see all the different possibilities for constructing a rational expression like this. Okay? So as we work through examples, we're going to just do a couple simple examples, and we're only going to worry about something that's repeated once, only about a repeated factor where 2 is the power that we see. So this will be the form that we're going to look at in our examples. We'll start with a rational expression like this with a repeated linear factor. We'll propose the decomposition. We'll convert to a polynomial. And then we'll solve for the amounts a, b, and c that appear. Okay? So as a first example, let's fill in something that looks like this. So let's pick a choice for p and q and then try to find the correct partial fraction decomposition of that. So let's look at 1 over x, how about x minus 1? So I'm choosing that p to be negative 1. And x plus 2 squared. Right? So that's my starting rational expression, and I want to perform a partial fraction decomposition to split that into pieces. Okay? So I propose a decomposition based on this pattern here. We're going to allow a piece that looks like a over x minus 1. Since that's only to the first power, I only need one piece in my partial fraction decomposition. And then for the x plus 2 squared, we're going to give ourselves two separate pieces, b over x plus 2, and a second term for the x plus 2, which will be c over x plus 2 quantity squared. Okay, so this is the partial fraction decomposition that we want to propose. Our job now is to figure out the values of a, b, and c that make the left side of this equation equal to the right side of the equation. As long as we set up the pieces in the right way, we should be able to find a unique way to do that. There should be a way to pick single values for a, b, and c so that this pile of small things is equal to this big one complicated thing. Okay? All right, so the next step, once we've proposed our decomposition, is to convert to a statement about polynomials. All right? So I want to remove the denominators everywhere in this equation, and the way that we do that most efficiently is by multiplying by the denominator of the expression that we started with, the big complicated one. So I want to multiply both sides of this equation by this whole denominator over here. I want to multiply by x minus 1 times x plus 2 squared. And that pattern is going to cancel out with some of the pieces on the right-hand side. On the left-hand side, it's going to make the denominator completely disappear. All right, and this will give us a polynomial statement that we can use to figure out a, b, and c. Right, so multiplying both sides by this denominator leaves us with 1 on the left-hand side. And now, when we multiply that denominator times a over x minus 1, the factor of x minus 1 is going to cancel out. We'll get 1 in the numerator, 1 in the denominator. Those cancel perfectly. And that leaves us with this x plus 2 squared in the numerator. So I get 1 is equal to a times x plus 2 squared. And the next term, we get one copy of the x plus 2 is going to cancel out, but there'll be one left over when I multiply by x plus 2 squared. So the b will be multiplied by x minus 1 and one copy of x plus 2. Okay. And then finally, when I multiply this last term, c, by the denominator x minus 1, x plus 2 squared, the x plus 2 squareds cancel, and we're left with just a copy of x minus 1. Okay, so we've proposed our decomposition. We've multiplied by this denominator to give us a statement about polynomials. And now what we want, what we're looking for, are the values of a, b, and c that make the left-hand side equal to the right-hand side for all values of x. And the way that we usually do this is to cherry pick the values of x, to pick the sneaky values of x that give us really, really simple relationships or information about a, b, and c. We look at the factors that appear, and we want to select the values of x that make one or more of those factors equal to 0. Okay? So in this situation, we can choose x equal to 1 will make the factor x minus 1 equal to 0, and x equal to negative 2 will make the x plus 2 factor equal to 0. Each one of those will give us a very, very simple equation that gives us information about a or b or c. Okay, so we go ahead and do that. Let's start out by picking x equal to 1 and looking at the information that we can get from that. So 1 is equal to, if x is equal to 1, the b term cancels, goes to 0, and the c term goes to 0. So the only thing that's going to be left over is this a term. X is equal to 1, so I get a multiplied by 1 plus 2 is 3 squared. All right? So choosing that value of x gives us the value of a. We get an equation we can solve to tell us what a is. 1 is equal to a times 3 squared. 3 squared is 9. So 1 is equal to a times 9. And if we divide both sides by 9, we get the value of a. A should be 1/9. Next, we'll check the next sneaky value of x that makes some of these factors cancel perfectly. And the choice that we want to make there is x is equal to -2. Okay? So if we substitute x as -2 into each one of these terms, the a term is going to cancel, the b term is going to cancel, but the c term is going to be left around. So substituting x equals -2 everywhere, we get 1 from the left-hand side. The a and the b cancel, and we're left with c multiplied by -2 minus 1. C times -3. If we solve that equation, it gives us the value of c. C is equal to -1/3, or 1 divided by -3. Same thing. Okay. So now something a little bit more complicated than our previous examples happens. We've run out of x values that kind of make things cancel out. We've chosen both x values that make the factors in this denominator go to 0. But we haven't yet found enough information to tell us the values of a, b, and c. We know a, we know c, but we do not know b yet. So it's now up to you to make a choice for what x value you want to plug in for some more information about b. You can choose any x value you want that's not equal to one of the things we've already tried. You just need to plug in a different x value and see what that's going to tell you about b. Some good choices: you might try simple values of x, like x equals 0 is often a nice choice. X equals 1 we already tried. You might try x equals +2, x equals -1. Anything that you want to help you simplify and deal with the algebra. What I'd like to do is pick one value and see what happens. So if I was going to choose here, I would try to choose x equals 0. By choosing x equals 0, it'll make the algebra a little bit easier than if I have to add or subtract an x value to the other things that appear in the factors here. So let's try this out. X equals 0. If we substitute this into the equation and we substitute the information that we already have about a and c, then we should get an equation that tells us what the value of b should be. Okay? So plugging in x equals 0 everywhere, we're first going to see 1 is equal to a times 2 squared plus b multiplied by -1, that's the x minus 1, then multiplied by +2, that's going to be the x plus 2. Finally, we get c multiplied by -1. Okay? So we've substituted in x equals 0 everywhere in this equation. And next we're going to plug in the values that we know for a and c, and we'll end up with an equation that tells us about b, gives us the value of b. So 1 is equal to, a is 1/9, 2 squared is 4, so we're going to see 4/9 here. The b term, if we multiply -1 times 2, we get -2. So we can write this as -2b. And then finally the c term has been multiplied by -1. And c was a -1/3. So we can take -1/3 multiplied by -1, and we would end up with +1/3. Okay? Now, we have kind of a messy equation, but one that we would like to solve for b, to get b by itself. To make the algebra as simple as possible, I think the first thing I would do would be to try to introduce a common denominator between each of the constant terms. If I can write all of those constant terms as in terms of a common denominator, then we'll be able to combine them together into a single number. All right? So if I write each of these things with a common denominator, so 1, if I want to write that with a denominator of 9, I can multiply by 9 over 9. Okay? So 9 over 9, that's equal to 1, is equal to 4/9 minus 2b. And then 1/3. If I want to write that with a denominator of 9, I can multiply top and bottom by 3. So this is plus 3 over 9. Right? So now by looking at that in terms of the common denominator of 9, now we can combine each of the constant terms, and addition of those fractions won't cause us any extra difficulties. So we have 9 over 9. Here I have 4/9 and 3/9. If I use the commutativity of addition, I can change the order and kind of put those two things together. So 4/9 and 3/9 gives me 7/9 minus 2b. Okay, and now if I want to solve this equation for b, to get the value of b alone on one side of the equation, then I would subtract 7/9 from both sides. So 9/9 minus 7/9. We'll be left with 2/9. Right? 9 minus 7 gives us 2, and these are the same kind of thing. And that's supposed to be equal to negative 2b. To finish solving this equation, I need to divide by the coefficient of b. That'll get b by itself. So I want to divide both sides by negative 2. Dividing by negative 2 is going to cancel the 2 in the numerator. Dividing by this negative 1 is going to introduce a negative sign. So this last step of algebra tells us that b should be equal to negative 1/9. Okay? So that's quite a bit more work than we saw in the previous cases, because we ran out of these sneaky x values that gave us the values of a, b, and c directly. We had to do some algebra and take into account some information that we already knew to figure out what the value of b was. All right? But again, we're now done. We've completed the partial fraction decomposition. So we had this starting rational expression with a repeated linear factor. Because of that repeated linear factor, we introduced 2 pieces into the partial fraction decomposition. One piece with each power of the repeated factor to the first power and the repeated factor to the second power. Then, once that decomposition is proposed, we converted to a statement about polynomials, and then we used different values of x to tell us how much a, b, and c should be, what their value should be. We cherry-picked the values of x just like we did in the regular non-repeated linear factor case. And each one of those values of x gave us one of the coefficients a, b, and c that we were trying to find. And then finally, we needed to choose yet another value of x so that we could get enough information to get the value of the last coefficient b. So in general, when you propose a partial fraction decomposition, you'll have a certain number of terms, a certain number of pieces. You'll have a certain number of coefficients, in this case a, b, and c. We have 3 amounts of each of those pieces, and we're going to need to use that many x values to get enough information to figure out all of their values. When you choose the x values in this sneaky way, it makes the algebra as simple as possible. When you run out of values that you can use that really simplify the algebra, choose something else that's simple and easy enough to compute. Okay? And then just carefully plug in all the information that you have and use the resulting equations to solve for the coefficients that remain. Okay? So if you substitute 1/9 for a, negative 1/3 for c, and negative 1/9 for b, then what you'll end up with is something that's equal to this this rational expression that we began the process with. So that's how you handle a repeated linear factor in a partial fraction decomposition.